In this short video, we will write down all information we need for writing a code simulating a single effect evaporator. This preparation step is key in programming. If you start programming without being sure what you want to do, it is very likely that you will waste a lot of time. The code we are aiming to write will be very similar to your starting point in the compulsory task, where you should change the code into a more advanced code for a multi-effect evaporator. But for now, the task we should solve is as follows. Design a single effect evaporator to concentrate 1 ton per hour of gelatin solution from 5 to 25%. The pressure in the evaporator, that is in the condenser, is 1 bar and 2 bar pressure steam is used for heating. The feed is at 80 degrees centigrade and the heat capacity for gelatin can be assumed to be the same as for water. Assume that the boiling point elevation and heat losses are negligible. Determine the area needed if the apparent overall heat transfer coefficient is 1.6 kilowatt per meter and Kelvin. Before we start programming, we should choose suitable variable names and carefully write down the equations that we should solve. For a single effect evaporator, these equations and the variable names we typically use should all be familiar to you by now. To simplify our programming efforts, we can reduce our number of variables slightly. In a well-functioning evaporator, all incoming steam condenses and thus S equals K. We can therefore replace the condensate flow variable K with the steam flow variable S. We can also assume that the temperature of the condensate is the same as the temperature of the steam and thus replace Tk with Ts. Mass and energy balances are central for describing a system mathematically, and for a single effect evaporator we have 2 mass balances and 2 energy balances, thus giving us a total of 4 equations. Let's extract the known variables from the text. We have that F equals 1000 divided by 3600 kilogram per second, XL is 0.25, XF is 0.05, temperature of feed is 80 degrees centigrade, pressure of steam is 2 bar, that is 200 kilopascal. The pressure in the condenser is governing the temperature of the V&L flow is 1 bar, that is 100 kilopascal. And finally, the apparent overall heat transfer coefficient, K, is 1.6 kilowatt per meter in Kelvin. Remembering that enthalpies can be calculated from temperatures and compositions, that leaves us with the following unknown variables. Liquid flow L out, vapor flow V out, steam flow S, and heat exchanger area A. We thus have 4 unknowns and 4 independent equations. As you might remember from your mathematics courses, this means that we have a solvable system. To solve the equations numerically, we will rewrite the 4 balances, the 4 equations, in residual form. That is, move everything to the right side and call the left side the residual. By doing this, we can make guesses of unknown variables and know that the closer to 0 the 4 residuals become, the closer we are to the correct solution. As we will need many guesses to find the solution, we put the equations into a separate routine. We will, as stated above, also need equations or routines for calculating enthalpies. In this case, we have provided 3 routines for you on the course web. HSteam for calculating enthalpy of steam, TS from PS for calculating the steam condensation temperature from the steam pressure, and finally HL gelatin for calculating enthalpy of liquid solutions of gelatin. The task states that we can assume all liquids to have the same enthalpy as pure water, but by moving this assumption into a separate routine, we can easily change that assumption later if we want to. For sake of consistency for liquid enthalpies, we will use the routine HL gelatin to calculate enthalpies for pure liquid water as well. The HSteam routine needs temperatures as input, and we currently have the information on the steam given in pressure units, so we need to translate that into temperature units within our code. We could perhaps have used Antoine's equation for that, but we have provided routine TS from PS for you instead. So we have HT, a function of T saturation and T actual, gives us enthalpy of saturated or overheated steam. HL gelatin, function of X and T, gives us enthalpy of water solutions of gelatin, and Ts from Ps as a function of Ps gives us condensation temperature given the steam pressure. We now have a graphical overview of our system, the names of the variables we will be using, the equation system to solve in residual form, a list of all our known variables, a list of our unknown variables, as well as a list of other equations that we will be needing. Let's write this information in plain text to use as a starting point for programming. With this preparation, we are now ready to start programming. Our first step in programming is to check that we understand the routines provided.